Hello, Mustangs. Today we are going to be looking at data sets, bivariate data sets, and trying to determine if they're linear, and also just describing the pattern that you see in front of you. So it's bivariate. The first condition that you need to look at is, do you have quantitative data? It's not categorical. So when we do these sets, that's the first thing. You wouldn't be able to graph it anyway if it was categorical. It wouldn't make sense, right? We're going to try to determine if trying to fit a line to the data is a good idea. And we're also just going to be describing the data. I'm also in this video going to show you how the correlation coefficient R is calculated from that. So here we go. This first set is performance versus brain size. So I'm going to just insert a data and statistics page, and on the x-axis I'm going to put brain size. And I just got these out of the textbook. These are just textbook data sets, and then performance. So they're trying to say, the bigger your brain, the better your performance, or something like that, seeing if there's a correlation going on there. Remember, we use the words correlation and association. We never really try to say it causes, like, oh, the bigger your brain, causes you to have a better performance or something. We just say there's an association. How strong is that association? And that's kind of the things we're trying to do. We do have this sheet. It's in the Google folder. You can find it there in the notes and stuff. It's a kind of a shorthand way of how do we describe bivariate data. Remember when we did univariate data, one-dimensional data, we had the big three. We had center, shape, and spread. When you do bivariate data, it's the same thing. There's a little more to it, but it's almost the same. So the center of that, you're just trying to say, is it a positive trend, which is, it goes up? Is it a negative trend? It goes down? Or is there no trend at all? So that is the same thing as your center. What's the pattern doing? So as your x value gets larger and larger, is your y value also getting larger? Or as your x value gets larger and larger, is your y value getting smaller? Okay, so that's center. The shape of this thing, I'm going to go down a little bit to the pattern. So the pattern would be considered the shape. So is it linear pattern? Is it curved? If so, is it exponential or whatever? And you might be able to figure that out. But really just saying, is it linear or curved is enough in this class. Or really there's no pattern going on. It's just there's no association. Okay, so that's your shape. And then the spread, I would say, is your strength here. So is it a strong correlation where things are really tight together? So the spread is not very much. Or is it moderate where you have a little bit of spread going on in your data? Or is it a weak association or weak strength where the spread is quite large? Okay, so that's your center, shape, and spread. Now remember when we did the big three before, we had unusual features. Do you have an outlier? Is there a gap somewhere, right? That kind of thing. So now in bivariate data, we also have the same thing. Do you have unusual features? One unusual feature you can have is fanning. Does it fan to the right? Does it fan to the left? Where the variability in the beginning is not as much as in another location, which we call that fanning. Fanning is not good. If you have fanning, you're not going to be able to fit a line to it. It's not a good idea. You can't use a line very well because the pattern doesn't quite fit. When you make predictions, this is kind of getting way ahead, but way down when we start doing predictions, then you're going to notice that the zone of prediction in the beginning here is different than the zone of prediction in the end. So you can't use the same model, right, for this type of data and that type of data. So fanning is no good. Also, any of these things, like do you have an outlier in the X or outlier in the Y or outlier in residuals? That's no good either. So if you have some kind of what we call an influential point, and we're going to get to exactly what that means and more of a discussion about that in a couple classes from this video. So look for more videos on lessons and problems that deal with influential points a little bit later. Today we're just kind of trying to do the big three and saying, could I fit a line to it or not? And just kind of describing data in general And we're also, like I said, we're going to look at the correlation coefficient. Okay, so my first set of data, like I said, we had brain size and performance. When I try to describe this, I'm kind of like thinking, well, it's all scattered all over the place. I don't really see much of an association. So when I go through that big three, the center, if I were to try to put a line in there somewhere, does this go down or go up, or is it flat? It's really hard. So I would probably say there's not much or no association. You can say, it doesn't look like there's much of an association at all. And that's fine. It's just, I don't know, it's probably flat, right? So that's center. The shape of this thing, again, it's not very, it looks kind of just a blob. So there really is not much shape. It's hard to describe that. It doesn't look really necessarily curved, but it doesn't really look linear either. So not a lot of shape. And spread is very spread out. You can talk about numbers. It goes from 70 all the way up to like 150 in the performance, all over, no matter what your X value is. So for low values of X and high values of X, the spread is high. For the higher values, it does go from 110 to 150, but from like 700,000 up to 980,000, it's from 70 all the way up to 150. So this one you wouldn't really have much to go on. You wouldn't really talk much. You probably wouldn't try to fit a straight line to this. You could, like you can always just do it. Go to analyze, put in your show linear, and it'll put it in. So it does kind of have a positive trend, according to the numbers, but it's just really, really low association, right? When you talk about spread, you're talking about, is it a strong, moderate, or weak association? This is a weak association, and I want to get the R to show up on this. So what you can do, I got to get diagnostics to pop up right here. So diagnostics. If you're noticing the R squared is not showing up on when you do a regression, this is where you want to go. So you see how that popped up? Let me do it again. You go to settings, and in your settings right here is your diagnostic button. Okay. And just say, okay. And then I have my R squared here. Now this is R squared, not R. So I'd have to take the square root of that, but you can see it's a low number. It's really small. So I have it's another indicator that I have a really low correlation, but honestly, I didn't need it because I can see it's a low correlation. But you do have to be careful, because what if I just take this axis and I squeeze it down? Oh my goodness, what happened? Well, you can see my R squared didn't change, my equation didn't change, but my perspective changed. So some of you might have looked at this data in the beginning, like, let me get rid of this. Whoops, I think I can just delete it. So I'm going to get rid of that. If I would have shown you this in the beginning, you might have said, oh, look, it has a strong correlation, blah, blah, blah. Why do I know that this doesn't have much of a correlation? Why? Because if you look, the trend of this is very horizontal. It just goes straight across. It doesn't go up, it doesn't go down much. And that's one of the needs to have correlation. If you have correlation, it's going to go up or it's going to go down. To have perfect correlation, it's going to go up the same amount that you go across. So if I go over 1, it goes up 1. If I go over 100, it goes up 100. If you have negative correlation, that means if I go over 100, it's going to go, like a perfect negative correlation will go over 100 and down 100. So you'd have like exactly 45 degrees going each way. This is really flat. So we say there's, like, even though it looks like the variability is strong, we still say there's really no association, there's no correlation, because as my X value changes, my Y value doesn't change. The X value doesn't affect what my Y value is because it's just flat. So when you talk about correlation, don't just look at how tight it is. You're also looking, is it flat, or does it go up, or does it go down? That's actually more the main thing about correlation. Okay, so that's a good description, right? That's a lot of good stuff right there. Let's try another set, see what that looks like. This is Kentucky Derby winners. So we have the year, and we have their speed in minutes and seconds. that was combined to make a total speed, and then a total time, and then we also have the speed here. So let me add in a insert a data and statistics page. Now I'm going to put the year on the bottom. Whenever you have something like the year or the day or the month on the bottom, you are creating a time plot. So, a time plot is nothing special except for the year. It's like time on the x-axis, right? So let's put in the just total amount of time it took them, see what that looks like. Okay, now that one's a little curved, isn't it? Let me move this over so we can see it a little better. Okay, so you can see it's curved right off the bat. I can see that. I can see a couple other things. I see this group going on. This group of data is kind of separated from this group of data, isn't it? Like it's a little bit different. It's got its own little kind of place. So these are things they want you to mention. We want you to mention. So let's go through them. Center, shape, and spread. Center, shape, and spread. So where did my sheet go? There's my sheet. So remember, I want to start, is it positive, negative? I want to know, is it linear or curved? And I want to know, is it strong, moderate, or weak? And then I can talk about any unusual features like fanning or outliers. Okay, so let's go back. I would say like the center of this thing, it is going down, right? So as my X value gets larger, my Y value is decreasing. So that would be my center. And you just say it like that. You say, well, as X gets larger, the Y value decreases. That's all. That's good enough for center. The shape of this thing, it's curved. It looks like it has kind of a decreasing or a decaying kind of exponential pattern. Like decaying is a good word for exponential. And then also the spread of it. It's kind of a moderate association, right? It's not really spread out, but it's not really tight either. It's kind of a moderate to strong maybe association. And you can say that, moderate to strong. That's okay. You can say that. This does have unusual features. It has a gap in the middle of these two data sets, which makes me think there might be something going on. Like, is there something about the race before like 1896 or something? Like, what is this point? Yeah, 1896, and this point is 1895. So from 1895 to 1896, did something change in the race? And if you actually go look at the data, you're like, go look at the race and look that up. The length of the race changed from 1895 to 1896. So that's what you're seeing here, is you're seeing that gap because the length of the Kentucky Derby actually changed. So these are actually two different races because this is a longer race than this one is. So obviously it took longer because it was a longer race than this one was. So the gaps will usually tell you something like that, like maybe men and women data are mixed, like the height of a man and height of women. You're mixing that data and you're going to see this kind of this double group, right? Stuff like that. So that gap is there for a reason. So in reality, like if you were doing this in the real world, then I would separate this data out. I would take this data on the left and make my own plot for that. And I would take the data on the right and make my own plot for that. And if you're trying to use a model to make predictions and stuff, like in the future, I'd probably be using this second set of data, not the first, right? Because this is the old track, right? So you kind of want to break those up and have two different analysis for those. Okay, so that's unusual features. I don't see any fanning really, but it's that gap that's really important. Okay, and that would be it for describing it. That's enough. Let's go to next. This is roller coaster speeds. Insert data and statistics. We have the drop in feet, like how high that first drop is on the roller coaster, and then miles per hour. So obviously the drop is what's going to affect how fast it goes. The bigger the drop, the bigger the more speed you're going to have, which is what we're seeing here. Okay, now this looks like a something we're used to seeing, where you get a normal pattern, a normal linear pattern. But let's just go through it. So what's the center? It has a positive trend. As my X value gets larger, my Y value is getting larger in general. It has a linear pattern. It's not really curved. I mean, it's not perfect, but it has a linear pattern to it. I can go ahead, let me put my regression on there, analyze regression, and you'll see my R squared comes up. And then for the spread, I can say it has kind of a moderate spread, maybe moderate to strong. I can see that this R squared is 0.82. So that means if I take the square root of that, I'm like at 0.9, right? Sorry. So 0.9 squared is like 0.8. So that's pretty strong. So this has a moderate to strong correlation going on. Unusual features. Does it fan left or right? Not really. I mean, there's a couple little stray points here and there, like these down here and these up here, but it's not really a big general fanning going on. So don't overdo it and say, yeah, I see this little fan down here. You don't want to overdo it and overcook it. All right, just it's kind of a moderate to strong correlation, and that takes care of these little dots here and here and here. I wouldn't really call these outliers. They're not so big that they're bigger than my maximum and bigger than my minimum points. So you don't really call them outliers technically. Outliers really need to be unusual. They're going to really affect the line. And let me show you this just so you see it. We're going to do this again when we talk about influential points, which is in a later lesson. But if you're curious, like, is this an outlier or not? If you grab it and you move it, notice how the equation of the line, I mean, you can just watch the line, not the equation, just watch the line. The line it wiggles a little, but it's not really moving much. Like this point really doesn't influence things very much. If I grab a different point and move it, oh, sorry, I should have undone that because I don't want to change my data. When you move a point, you change the actual data, and I didn't want to do that. Okay, so let me grab a different point and move that one. You see how the line moves more? Still not a lot in the middle, but the ends of it move quite a bit. So this would be more of an influential point than that one would, just because it's so far away from the center. But it's not an outlier. I mean, it's right in line with our line, so it's not really an outlier. Okay, so I don't really have any fanning. I don't have any influential points. It's just a normal, pretty linear set of data. There is a pattern going on, so it does have correlation. There is an association between the drop height of feet and the miles per hour of the roller coaster on that first drop. Okay. Now I'm going to show you how R is calculated and show you how R squared is how R is calculated, and then I'll be done. So that's the last thing I'm going to do is show you how R is calculated. Okay, so I've got two data sets. I made one that's like perfect correlation R. So if you're like, how do you get a perfect correlation of 1? Remember we said the correlation goes between -1 and +1, the correlation coefficient, right? So how do you get that perfect one? Well, what it is it's calculating a percentage. It's a percentage kind of idea. So what happens? Well, we take our data sets. I just made up like perfect data set, something that would be perfectly linear and would have a correlation of 1. So I made those up here, A and B. And then what I did is get the one variable stats from those. So one variable stat on both of those. So I have the mean of both sets, and I have the standard deviation of both sets. And then the next thing I did is I found the z-scores of both sets. So these are all the z-scores of set A, of your x-axis, and these are all the z-scores of the y-axis separately. You do the z-score of A and the z-score of B separately using the mean and standard deviation. You can see my equation down here at the bottom. It takes every single data point, subtract the mean, and divide by the standard deviation. That's getting a z-score. That's getting your how far away from the center you are in terms of, it's like standardized, right? Okay, so I actually graphed that out. So you can see the ZA on the bottom and ZB on the left. So these are in, the scale is in z-scores. So for like this point, if I go over 0.49 Z, right, standard deviations, it's also going up 0.49 standard deviations. This one's going over 1.48 standard deviations and up 1.4 standard deviations. So if those z-scores match up perfectly, then you're going to have that perfect line. And then like the next step for R is to take all your z-scores in the X list and all the z-scores in the Y list and multiply them together. So actually what you're making is a bunch of rectangles. So here I would be taking, here I would be taking, like this point would be 0.165 times 0.165 and getting a rectangle down in here. And this would be doing over 0.495 times 0.495 and making another rectangle. And that area, all those areas get added up. So over here, I added up all the areas in this list. So all the areas added up is equal to 9. And because this came out to be perfect correlation, this sum came out to be perfectly 9 because I had 9 data sets. It's really weird to think about, but it actually works out perfectly. Some will be below 1, some will be above 1, but when you like add them all up, it'll equal the same number of data points. Well, actually, the same number of data points you have minus 1. Really weird, really weird. I've spent days trying to like wrap my mind around that, but we can talk about it one-to-one if you want. But, okay, so this comes up to exactly 9 because it was a nice, perfect, exact set. And then you take the average of it. So I had 10 data points. So I take my 9 divided by 10 minus 1. So 9 divided by 9. And I got a perfect correlation of 1. And it works that way. The process works that way every single time. That's how R is calculated. So that is R. R is 1. It's a perfect correlation. Now I did another set that wasn't perfect. I just took an actual set of data. This is actually the roller coaster set of data. So I took the drop and the miles per hour. I did a one variable stats, got the mean and the standard deviation of both sets. Then I did the z-score of each set separately. So this, you can see the equation, the drop in feet minus the mean divided by the standard deviation. So that's a z-score in the x direction. And then the z-score for the y direction, miles per hour, minus the mean divided by standard deviation. And I get a z-score for all those data points. I multiply those together to get rectangles. Right? So here's all my z-scores, right? Original data, z-scores. Notice the distribution and the pattern of the points are the same, but now my center is right at a z-score of 0, 0. If you think about it, the mean of a data set is always right in the middle of the data set. So the mean of my x's is right where the z-score is going to be 0. And the mean of my y's is right where the z-score is going to be 0. So the center of your z-score graph is always right in the middle of all your data. And this is something you should really put in your head because this comes up in questions. This kind of idea, like where's the center of a set of data? Well, it's where the mean of your x and the mean of your y is, because the z-score for each of those is right in the middle, right where the mean is, right? So the z-score is 0 right there too. Okay, so that's just a kind of a sidebar. But anyway, so every single data point, like let's take this one so you can see with me, it's 1.845 times 1.67, and I'll get a rectangle area. And then I'll take this point, and I'll take negative 0.266 times 1.42, and I'll get a rectangle area. Now keep in mind, this one has a negative in it. So when I multiply, it's going to give me a negative area. This is important. Why? Because when you add up all those rectangles, remember the next step is to, you can see that at the bottom down here, I'm going to add up all these rectangles. I'm going to add them up. Some of those rectangles are negative, some of those are positive. So because some of those are negative, it's taking away from my total correlation, and it's lowering the value of my correlation. So for anything, any point that's up in the first quadrant and the third quadrant, it's going to give me positive correlation. Anything that's in the second quadrant and the fourth quadrant, those are going to be negative correlation. So if you had, so then it's a balance, right? You have positive going one way and negative going another. So, how much of this is positive correlation and negative correlation? And so when you sum those all up and you average them, you're just saying, what's the average association? Is it positive or negative? So here I have more points that are in the positive direction than I do have points in the negative direction. So overall, I have a positive correlation. It's It's all just comes from z-scores. That's where it all comes from. If I had a bunch of points going this way, I would have more negatives than I would positives. The R value would come out to be negative. You'd have a negative R because you'd be adding a bunch of negative areas. Hopefully that makes sense. Okay, that's where R comes from, right? In this case, we had a 0.9, so it's still pretty strong, right? And I can do a correlation to match that up. This is the same R that the calculator calculates it, and this is how the calculator does it. Okay, let me know if you have questions ever, eh?